Let's call it the practical formula. Or integrating. In Finnish, we use against, or I don't know if that's proper English, but in Finnish we might integroida jotakin vasten, integrate against something. So now we would say integrate against the law. Okay, so what is integrating against the law? It is nothing illegal, don't worry. It is, let's recall, we have this abstract setting and probability measure here. We have a random variable, which is a map measurable from omega to the real line. Then we define the law of x. We defined it in this way. It's a set function that gives a Borel set the value probability, the pre-image of the Borel set. And we often write this informally as probability x belongs to B. This is a kind of intuitive shorthand for this precise definition. And this is defined for every Borel set B. And we learned that P of x is a probability measure as well. It's a probability measure on the real line equipped with the Borel sigma algebra. So essentially, what's happening now is that that's the abstract space. You could think, remember, P is now kind of the joint distribution of everything, and then we map kind of from here, and there's a new space that we are observing one random variable. So we observe the real line and the Borel sets, and then we have another probability measure in this part of the world. So this is the law of x. And somehow when we only care about that one random variable x, then we want to kind of, we might actually ignore this omega, and we could think of working on this part of the world only. This one gives us all the probabilities associated with x. So this should be enough to calculate the expectations of x as well, this measure here. And is that doable? Yes, we can calculate all the expectations of with this measure. So let's do a theorem. For any Borel function phi, so it's a function from real line to itself, and assume that phi is non-negative. So then for any such function, we claim, or I claim, that if you want to calculate the expectation of phi of x, so this is another random variable. We take a random variable and function. This is kind of a new random variable. You might denote it as y. And you can ask, okay, how to calculate the expectation of this? We know that by definition, the value by definition, this expectation is the integral of y against the measure p, which we also know that it's the integral of phi composition x integrated against p. This is by definition how the definition goes. But in practice, we might think that can we calculate this expectation of y, or this phi of x, using this law, the distribution of x? The answer is yes. So the answer is that yes, this is possible. We can integrate over the real numbers, phi of just normal real number. We use the law of x and we integrate against this. So let me put dx in parentheses to indicate this. Okay, in shortly, we would just write phi d bx. This is what the theorem says. Is that sensible? Let me sketch a bit of a proof. Why should this be true? Assume in all of these type of questions is something true like this, so it's good to start with simple functions or indicators. So assume first that phi is an indicator function. So let's assume that phi is an indicator of a Borel set. For B being some Borel set, so it takes values 0 and 1. And let's see, would this be true? Would this be true in case phi happens to be indicator of a Borel set? Let's do the calculation. What's on the left? The left-hand side is equal to expectation of phi of x, and it's also the expectation of indicator that x belongs to B. So it's actually x pre-image B indicator. That it's the expectation of this. So, and we know that the expectation of an indicator is always the probability or the measure of this thing. But this is by definition the law of x for the set B. On the other hand, what is the law of x for B? So then that's also the indicator of B, integral of indicator of B against this measure now. And then we remember that phi was indicator of B, so this is integral of phi dpx. And yes, there it is. This is the right-hand side. If let's open what we wanted to prove. We wanted to prove this red star. If phi happens to be an indicator of a Borel set, this is true. What if phi happens to be a linear combination of indicators? Well, we have linearity here, linearity on the right. So by linearity, both things work also for. So first case was that we assumed phi to be this sort. And that was the proof. So let's take the proof away. The second part was we assumed that phi is a linear combination of indicators. And then linearity gives the proof of the claim. This was what we did. Third phase would be phi is Borel measurable and non-negative, and then the approximation that we used in the previous lecture, that we approximate by simple function from below. That monotone approximation gives the proof there. And last part is that phi is well, no, that was it actually. That this was the last part. What we wanted to do. We wanted to look for any general measurable and non-negative function phi, this formula.